Hi folks, this video playlist is particularly useful for people who are either new to 3D experience or are ABAQUS users and would like to transfer or transition to the 3D experience FEA solver. I want to remind you that the 3D experience's native FEA solver is actually the ABAQUS program. Now, what I do in these videos is I take a particular tutorial that is done on YouTube, it's available on YouTube, and the person who's making it is using the Abacus CAE to solve that problem. So I try to retrace, whatever is possible, retrace the steps that are done in 3D experience to solve that particular problem that is done with the Abacus CA. Okay. Now, the details of the problem that I'm going to be doing in this segment is shown next. It's a plate with two holes. The dimensions are given here. And these two holes, basically, there are rigid bolts inside of them. There are bolts inside of them which are holding this thing and preventing the horizontal deflection of this particular this particular part. Now we are assuming that everything is elastic. The thickness of this part is 200 millimeter in depth into the screen. Okay, and it is actually done in a step-by-step fashion using the Abacus CAE in this by this individual, by this professor, and but he's using the 2D plane stress elements to solve the problem. And he gets results. So this is the actual link to that Abacus tutorial, and the results are like this. Okay. Now, he remember that we are not going to model the bolt. We are assuming that the bolt is extremely rigid. Okay, so basically, all that does is that it prevents the lateral motion. Okay. Now, in 3D experience, you do not have 2D elements. You don't have 2D plane stress or plane strain or axisymmetric elements. Everything is 3D. Uh, Now, it is possible to do a replicate a plane stress problem with shell elements. The problem becomes that when I try to do it with shell elements in 3D experience, the bolts, basically are surfaces. So it can be done, but it's a big hassle. So what I decided to do instead is, first of all, model the entire thing as 3D. However, I'm modeling only half of this plate, actually a quarter of the plate, because there's a plane of symmetry at the bottom of this block, and there's a plane of symmetry at the right side. Okay, so basically this is 1/8 of that geometry that you saw, and I've meshed it like that, so it's rather fine in the lateral direction. But I didn't want to take a long time, so I made it only three elements through the depth here. Okay. Uh, uh, Now the details of the meshing is done here, and also I'm using hard contact. So this bolt is modeled as an analytical rigid surface in 3D experience, and I'm not going to mesh it, but I will have to define it as an analytical rigid surface, and there's going to be contact between this rigid surface and that block, and that's going to be declared as hard contact. It means that it just does not penetrate it. And the results that I get are something like that, that the numbers are not exactly the same, but one should not expect it to be, because the other one is plane stress, and this is the three-dimensional calculation. Now, it is possible to model it with a bias as far as element goes. So if you do it like this, remember the plane of symmetry is on the other side. You get the stress distribution, which is a bit different from the other one. And here is the front view, And of course, the way it's done is that when it comes to defining the mesh, there is an edit parameter button here that if you click on it, it'll take you there and it tells you what kind of a bias do you want and the number of layers, etc. Okay, so I'm not going to do this thing, but I just showed you the result. There is some documentation. There's some documentation about the analytical ridge surface. You can see that here. It's very limited because it has to be an extruded surface or a revolved surface. There are some limitations as what kind of a profile you can use. There's a little bit more information here and more, and this is the last one. So obviously, if you decide to do this thing, it's a good idea to go through these carefully if you need it, and then hopefully you're going to be in good shape. Okay, so let's go ahead and do this. Let's see now. This is an assembly, so I already went to the assembly design workbench here, and I already created an assembly there. Okay, so let us insert our first part. Insert 3D shape, the 3D part in there. So this, I'm going to call this the plate. So properties, just so that I can distinguish it from other things, I'll call it the plate. Okay, and we're going to make it. It's fairly simple. So double click on 3D shape. On the vertical plane, YZ plane, I will sketch. Remember, we are doing half of this, and the depth is also half of 200. So half of this, basically, we're doing modeling this rectangle with a hole in it. Okay. So let me make a rectangle here, and I'm going to dimension it. This one is 200 millimeters. My units are already set to millimeter. This one is 45 millimeters. Okay, then we're going to draw a circle there. It's exactly halfway. The diameter of that circle, that's going to be the hole. The diameter of it is 15. And it has to be positioned properly. It's exactly halfway between these two for sure. And for dimension from, zoom in, from that. Okay. The dimension from this is blocking my view. So let me actually delete this. First dimension it. I could have hidden it. So this thing is 50 millimeter. 50 millimeters. Okay, and now dimension this. That was 15. 15. Okay, good. So we exit and we pad this thing by 100 millimeter. Now I'm in the generative shape design. So let me go to part design. Okay, so we go to essential. There is the pad, and I'll do it in the other direction. Doesn't matter. And 100 millimeters. Okay, very good. Let's create our material. So tools, create a material. I'll call it uh, a plate made out of steel. Okay. All right. So there we are. Plate made out of steel. Right click, apply, and we're going to apply it to this part. And then we're going to input the properties. So we go here, double click on this. It's structures, ABAQUS structures, ABAQUS multiphysics, mechanical, elasticity, elastic, 200,000 megapascal, Poisson ratio 0.3. All right, that's good. So why don't we do a quick save? Okay, now we're going to insert our second part, 3D part. I'm going to call this thing the analytical rigid. I'll call it rigid bolt. How about that? I'll call it a bolt. Okay, so let's make it. Double click on it. So on that YZ plane, I will sketch a circle. Now the bolt is going to go in there, right? So I'm going to draw a circle here. Okay, you can either dimension it or you can somehow use the constraint. For example, this control that you can say constraint define the dialog box and say concentric, or you could have dimensioned it. Okay, and the dimension of that is 14.6 millimeter. 14.6 millimeter. Okay, it's a little bit smaller, so exit. Now we want to create a surface here because we're doing analytical rigid surface, so we have to go to generative shape design, and we're going to do an extrusion of that particular thing that I made here, that sketch. So this is fine, and then in the other direction, I want to go by that entire length, which is 100 millimeters. See that? It comes out of the other end, right there. You can see that. It's right there. Okay, good. All right, while we are at it, let's change the color of this thing. So let me go here, right-click properties on the graphics, change the color of it, maybe to brown, so that you can see it easier, right there. Okay, now this is going to be an analytical rigid surface, and analytical rigid surface is defined by a surface that's here and a reference point. Okay, so I'm going to create a point. We'll create a point. This can also be done later if you wish. You can do it later too. Okay, while you're defining the analytical rigid surface. But here, might as well do that right now. So center of a circle, this circle. So notice that it does create a point right there. This is going to be used as the reference point for the analytical rigid surface. We don't have to put any material on it because it's assumed to be rigid, right? So let's do a quick save. Okay, good. So let's go to, this is pretty much done. So we go to structural model creation. When this thing pops up, make sure that you select both parts, and then you say OK. Okay. So now we go and go to the meshing tab, and using the sweep 3D mesh, you select it. The support is let me select for the support. We select this block. See that? And this automatically sweeps it between this source and that target. Okay, if you want to do it this way, which I don't want to do, you have to go and do the manual source target detection. That's good enough. And I'm going to put down 3 millimeters here and mesh it. And there are 3 layers, obviously. That is exactly what I had there. Okay, good. We have to do the 3D property. There's no property associated with that, so we go to Properties tab. This is the solid section, and from there you select your you can select your part, this part body right there. Okay, and then it picks the correct material and assigns it to it. Now, for the analytical rigid surface, you select the abstraction tab. There's the abstraction tab. Select that. And down here, you have several choices: analytical rigid surface, and the other one is rigid body. This tutorial, we're doing analytical rigid surface. You select it. For the for the surface definition, we select that extrude. Remember, we did an extrude. And for the point, select the point. Select this point that we created. Remember, it was at the center of this circle. Now, if you are having a hard time picking it from the screen, you can go and select it from the tree right there. Okay, so this is the reference point associated with that analytical rigid surface. Now, you will see that I may have to come here and flip the direction, okay? Because when it comes to analytical rigid surface, the direction normal to the surface, and if one doesn't work, you have to flip it. Yeah, so let's leave it like this. I'm pretty sure this is going to bomb out, and we're going to have to come back and flip this. Say okay. So we have our model, finite element model here, the solid properties associated with it, and the abstraction right there. Okay. Let's do a quick save here. Okay. So now we go to that's pretty much it. We're done with the structural model creation. Now we're going to go structural scenario creation. This is where we apply the type of analysis, the load, the restraint. Okay, in here, one selects the finite element model. The one that I just created. In this particular case, there were two of them, but that's because I made some changes and they're both sitting there. That's okay. So that takes care of this. So we go on the procedure, on the static step. Let's put down here initial time increment of 0.01 and a maximum time increment of 0.1. Okay. These all make sense to the people who have already done some kind of an analysis with 3DEXPERIENCE or ABAQUS users. These are exactly the same dialog boxes that appear in ABAQUS CAE. Say okay. All right, so as far as the restraints go, first of all, the bottom and the back side are planes of symmetry. So here, plane of symmetry. You turn it around. This is a plane of symmetry right there. And you have to do these things separately. And then another plane of symmetry on this side. Okay, good. All right. Now, I want to clamp this reference point, okay, because this is a rigid surface that it will not move. I'm assuming it will not move, okay? So we can use a clamp or we can use a, fixed displacement. Everything is fixed. So I'll use fixed displacement. This point, again, if you're having a hard time, zoom in there, and all 6 degrees of freedom are fixed. You can also use clamp. Okay, that's good. All right, now the load is translation of 10 millimeter on this side. So I selected the load. Here's a translation. You select that face. In the direction Y, the value of 10 millimeter, 10 millimeters. Okay, good. The final thing we have to do is to create an interaction between the analytical rigid surface and the hole and call it contact. So here's the interactions tab right there, interactions. First of all, defining surface spacing contact, you click on it. For the master surface or the main surface, they take the more rigid one, or the one that's finer in discretization. Now, we did not discretize this because it's an analytical rigid surface, but it is rigid. So for the main, we select this, and for the secondary, let me hide that extrusion. The hole inside, surface of the hole, is going to be the secondary surface. It is possible to swap these if you want, but we don't want to swap it. That's good. All right, and we say OK. All right. Now, we define the interaction. Now we have to say what kind of interaction is it. Are they tied together? Are they in contact with each other, etc.? So here's the interaction that was created. And now the contact property, you click on it, and it's a normal behavior, specify normal behavior, hard contact, and the default solver. All right. By the way, this cylinder, we hid it. It's still there. I don't have to bring it up, but if you feel more comfortable seeing it, okay, right here. It doesn't do anything. There. Now we're going to run this thing, but what will happen is that you'll see that actually this guy will cut through the rigid surface. So let's try it. Simulate, first do a model and scenario check. If there are any major issues, initially it's going to pop up here. Then we're going to do the simulation check. I don't anticipate any problems here. I'm planning to do the same video, not using uh, not using the analytical rigid surface, instead using rigid elements. Uh, we'll see that, but not in this session. This is a relatively simple problem. I can't even remember whether we did linear elements or parabolic element, but if you want to, it's just a matter of selecting the correct icon here. This is linear. This is parabolic. I can't remember what is it that I had there. Okay, this is done, and now come the moment of truth. We're going to run it, and I guess it will cut through that. I could not get it to, I could not achieve this thing, but in other problem where analytical rigid surfaces are not involved, it is possible to flip the direction of that normal. So if I go back here while this is working, if you go, yeah, there is that window that popped up, and you had to select the main and secondary, the secondary surfaces. There, there's an icon there. You can click on it, and it flips the arrows. So, but I could not get it to do that task for analytical rigid surface. That's why I will go back, and if it cuts through it, I'll go back and flip the direction of the arrow of the that flip direction checkbox there. Okay, this is done. All right, so close this. You can see that actually, if you look at the displacement right there, and this is the initial one, and the final one is right there. It actually cuts through it. Okay, so that means that the contact was not doing its job. So we go back to uh, scenario, and let's see now. There is that interaction that we saw. Analytical rigid surface. Where was it? In right here. Contact based contact based surface based contact. Okay. okay, not here. We have to go to, not here, we have to go, just 1 second, for a second. I want to check something. Yeah, see, this is what I was talking about. It flips the direction, but that's cannot be done here. So we go back to the abstraction. Abstraction. See that in the finite element model? These are your swept element. This is a 3D property. This is the analytical surface. Double click on it and flip the direction. All right, let's go back to scenario and run it. I don't have to check or check the model simulation because I know it worked. It's just that the contact was not actually in effect. One was cutting through the other one like butter, like knife cutting through the butter. Okay. Some of these tasks are easier to do in ABAQUS CAE, but of course, if you're transitioning, then you have to know how to do it in 3D experience, and the icons are different, the tree structure is different, some functionalities may not have been implemented. Yeah, it's not a piece of cake. It's not hard, but it requires some detective work and practice. If you look at the iterations, it's proceeding. Yeah, it has to go to 1 to finish. By the way, just like in ABAQUS CAE, if it doesn't go to 1, it aborts some intermediate stage, then you can still see the results prior to that. It's going very fast. It's a simple problem. It's extracting the results. Hopefully this time the plate will actually see the bolt. I think it does. You can see that. And if you look at the von Mises stress, for example, right there, you can see. Now, this one is different from the values that I have, legend that I have here. My guess is that here the element is linear. So actually, let's check that. Well, by the way, you can animate it if you want, and you can slow down the speed. Move this thing out of the way. Speed. Yeah, you can slow it down. You can see that it's building up. If you want to see your elements, incidentally, let me get out of that. If you want to get your elements, you click on this. You go to this tab here. See, contour plot. This tab, rendering. And say, show me the mesh. Shows you the mesh. Apply. Don't forget to say apply. It shows you the mesh. Now, I just wanted to check my element type to see whether it was parabolic or linear. So if you click on sweep 3D mesh, maybe we go to model and sweep 3D mesh, and oh, it is parabolic. So I'm wondering why are those numbers a little bit different. Let me see, I put my restraint here, I put the restraint there. Yeah, it could be that that particular mesh was not quite the same as the one that I have here. I'm not absolutely sure about that. So we say, okay. All right, that takes care of the tutorial. Good luck.